For this lesson, we're going to take a look at solving quadratic inequalities in one variable. When we're talking about a quadratic inequality, then we know that it's going to be a quadratic, like in the form of ax squared plus bx plus c. And it's going to be an inequality, so I'm going to, instead of saying is equal to 0, I'm going to say is less than 0, is less than or equal to 0, is greater than 0, or is greater than or equal to 0. Now we know they might not start out in this general form, but we can always take any quadratic inequality and turn it into this form by collecting everything on one side of the equation and balancing out for x. The first thing is we're going to look at how this could be interpreted through graphing. So whether I said that x squared plus 2x minus 8 is greater than 0, or x squared plus 2x minus 8 is less than 0, I can determine what range of values for x's would work for by taking the function for this, f of x is equal to x squared plus 2x minus 8. Now, when this gets graphed out on our graph over here, which we can see right here, the first thing that we're going to be looking for is we're going to be looking for those x-intercepts. We have the two x-intercepts that occur. One is at -4, the other is at +2. Then we can think of it, as we can see on the graph here, as when y is greater than 0, or the f of x part is greater than 0, or when y is less than 0. The x-coordinates of the points on the part of the graph which is above the x-axis give the solution to when it is greater than 0. So I can highlight what all those values are when it's greater than 0. And then I can state what all of the different values of x that would give me when that is greater than 0. And I can see that as long as x is greater than my bigger x-intercept, then my y value is greater than 0. Or if x is less than my smaller x-intercept of -4, the y value is greater than 0 for my function. If I want to think of when it is less than 0, then that's going to be when I have my function existing below the x-axis. That's all the values when y is less than 0. So when is that true? Well, it's still using the same intercepts, but it's going to be when it is between my lower intercept and my bigger intercept. And I can state it like this: when -4 is less than x, which is less than 2. So for my quadratic, there's actually two possibilities when it's going to be greater than. There's two separate regions that have a space between them. And I need to account for both those possibilities. I need to state that x is less than -4, or, and don't forget to say or because it's not going to be and, they can't be both at the same time, x is greater than 2. When is it true for when it is less than 0? That's going to happen when -4 is less than x, which is less than 2. We can see that the first solution can be represented on a number line showing that it is greater than 2 or less than 4. And don't forget they're using those open circles to indicate that there is no equal sign. So it's not true when it is equal to -4 or 2, but as soon as it is greater than 2 or less than -4, like 2.001 or -4.001, then it's true. The second possibility we can see exists between those 2 points. So here's the two ways that we could represent it. We can represent it on a number line, or we can represent it as a range of values. For the second example, we're going to do basically the same method to find what the solution region is for this inequality. 12 plus 4x minus x squared is greater than or equal to 0. And we're going to do that by graphing out the function that's related to this, replacing the inequality part and 0 with f of x is equal to, or y is equal to. So the first thing I'm going to put into my calculator is y is equal to 12 plus 4x minus x squared. I'm going to graph it out, and I'm going to find where the solution region exists on my graph. So when I graph it out, I'm going to get a quadratic function that's opening downwards, looks something like this. Doesn't have to be perfect. I'm going to have the points of -2 and 6 are my x-intercepts. I can state this is my function, f of x is equal to 12 plus 4x minus x squared. And I can see that when it says that it is greater than or equal to 0, that means that my y value has to be greater than or equal to 0. And it's going to be when it's above the x-axis here. Now, because this includes the equal sign, I'm going to make sure that I include solid dots, and I'm going to include the equals in my solution. So I can say that it's going to be when -2 is less than or equal to x, which is less than or equal to 6. I can draw this out on a number line as well. Having the point of -2 and 6, I got to remember to draw solid dots to indicate that it's equal to, and I'm going to shade in between those 2 points. If I was to state the solution when it is less than or equal to 0, then that's going to be the opposite possibilities. That's going to be when the y is negative, but it's still going to include that equals. So I can say that it's going to be when x is less than or equal to -2, or when x is greater than or equal to 6.